training session for prototype 1. This is work package 3 session 2. Okay, and we are going to have this agenda. Okay, there will be some question at the end of each main topic. Okay, so please, if you have some questions, write down your questions and then ask later, maybe at the end of the slot or maybe at the end of the main topic. Okay, first we are going to start with components, nominal and faulty behavior definition by Intex and Stefano. Then we are going to go functional early verification by FBK, MEDH, Pietro and Alberto, and then Irfan. Then safety analysis by FBK again, and the next topic will be safety case. This will be MDH by and Intex and FBK, and finally we are going to have a preview of what it's going to be the prototype number, prototype 2 P2, okay, by Bernard and Marner, Technalia and Honeywell. Okay, and that's it. We are going to start with Stefano. I am going to pass you presenting right center.
Okay, thank you, Luis. So can you see my screen?
Yes.
Okay. Perfect. So good afternoon, everybody. So the goal of this session is to continue with the to continue showing what we have reached in concerning the OpenSet prototype feature. So during this session we will introduce the features that we are proposing in order to particularly to cover the architecture-driven assurance goal of AMASS. So let's continue with the WP3 training by moving to a session to a slot dedicated to the specification of component nominal and fault behavior. So first of all, you can remember from the previous session that we addressed how is it possible to model the system architecture by using chess, and now the goal is to try to enrich the model with the information about the behavior. So the behavior can be of two types. The kind of behavior are possible can be specified in chess. The first is the nominal behavior, where basically the functional specification of the components provided, basically by using UML state machines as written here. And then it is possible to attach to the component a behavior regarding its faulty properties. And we will see this later. So starting with the nominal behavior, as I already said, it's possible to provide the nominal behavior by using state machine. The goal here is to provide this kind of information to then be used for analysis purposes, and in particular in order to allow the transformation and to perform fault-free generation by using the XSAP tool provided by FBK. So in order to support this transformation, currently we for the specification of the state for of the nominal behavior, we support a subset of what UML offers in the concerning state machine modeling, and then we require that in the state machine, when the actions, the activities that are expressed, and the guards that are expressed, in particular for state transition, has to be provided by using the new XMV specification language that is available online. So now I can switch to a demo just to show you how it's possible to create such and then edit such state machine. So let me just use a already filled model, at least filled for what regards the architecture specification, as we have already covered it in the previous session. So I can start showing the architecture of this system, which is a model of a battery system, where we have a LED, which is powered by a power system, which controls two batteries. So it is so in this system, the LED can be powered by one battery at a time. So we have a sort of redundancy here. So we have two batteries, one primary battery and one backup battery, which are controlled by the power system. And when as I said, a battery can power the LED, so only one battery can power the LED at a given time. And when a battery is not powering the LED, it is recharged by using a generator, which is also part of the system. So basically, this is the architecture, which is can be modeled by using the constructs that we have seen during the previous session. I'll also show some internal decomposition of the system. So I'm opening now the internal block diagram for the root entity. Okay, just a few seconds maybe. Maybe okay, some delay maybe due to the sharing the screen, I suppose. Okay, this is the internal block diagram of the power system, which, as I showed before, is in charge to control two battery. So and I can also show you this one, which is the internal block diagram of the root component. So here we can see how also the ports of the components and the connection of the components between these ports. So in particular, you can see that the generator as an input, an output port that is used from the power system in order to recharge the battery, and the power system is in charge to power the LED. And the LED has some kind of load information, which is used by a power system in order to estimate compute the energy of the current energy of a given battery. So this is basically an overview of the architecture. So let's try to check. Let's try to model nominal behavior of my power system block. For instance, we want to model the fact that the power system can has to switch between the primary battery and the backup battery in order to properly power the LED. So in order to create the state machine, I have to select the block in the Model Explorer, right click, select the new diagram, and then state machine diagram. Nominal, I can give it a proper name, nominal state machine. So here, okay, the diagram appears. You can find the palette on the right. You can see that we have a dedicated set of constants that are the ones that are to be used in order to then allow the generation to XSAP and so to support the fault tree analysis. And so I can just provide you an example of how entities can be created. As I was saying, I have to model the fact that the power system can be in a so-called primary state, where the primary battery is used to power the LED. Here, and sort of backup state. Sorry, backup state where the backup battery is used. I can model the transition, and I can specify the transition from one state to another. For a transition, I can, of course, provide information about when the transition is fired. Particularly, here we use the guard as the condition, which has to be a Boolean condition. And when the guard is true, the transition is fired. And then we can model the effect, so the action that are performed when the transition fires. In order to add the guard, I have to click on plus here and add the constraint. Then I have to create a new specification here and select opaque expression. So currently there are some steps that has to be performed manually, but we are thinking about to provide some extension in order to let the user avoid to perform these steps. And then for my expression, I have to select the language. Here I have to specify SMV. Okay. And here I can write the expression. In this case, I want to say that when the energy of my primary battery goes beyond a certain level, we have to switch. So here I can refer to the energy property of my primary battery in this way. And then I can, for instance, put a value here as a threshold. Okay. And okay, so you can see the guard here. I have used this primary bat because primary bat is the way my primary battery is referred in the context of a power system. So you can see also here that my primary battery in the context of our system is referred as primary bat. And then I can add an action here. So I have to select the transition, and now I have to create an effect. once again, select the opaque behavior and specify SNV. Now, as a effect, I can, in this case, I can put a condition on a property of this component. In this case, I want to specify that the property state of the component, which is a property, and I will show you soon, is to be put to backup. Okay, so as I would say, the state is a property of the block, which is an enumeration that can be primary or backup here. This enumeration is defined here. The same way I can provide information about the transition from the backup to primary in the same way as I did as I have just done for this transition. And this way, so I can provide the functional specification of my component. So let me just switch to the presentation. Now, let's introduce the default behavior, how the default behavior can be specified in chess. So chess comes with a dedicated dependability profile. So basically, chess concerning a given component, consider the fact that the component can be in an initial state, which is the healthy condition, and then a certain number of erroneous states can be activated, and when a state means that a given fault has occurred and it affects the internal state of the component. And then what we can consider is the concept of failure. So the error can propagate into a failure in the sense that the error is manifested in the interface of the component. So and so failures can possibly propagate through the output port of the component itself if the latter are connected to other components. Let's see how can default behavior can be specified in chess. So one possibility to use a dedicated state machine. So basically, an error model can be a fault behavior can be provided by a state machine attached to the component and stereotyped with a dedicated error model stereotype. Well, and in the state machine, we can provide information about the how a fault can occur, how they can originate in errors, and then how errors can possibly manifest some failures. And the error model, the state machine error model, is required in order to allow the invocation of the fault-free generation with the XSAP. Here you can see an example of a model state machine where you can, we can see some concept of the concept that I have introduced before are represented in the state machine. So we will see in details these in the next slide, but I can introduce here how internal propagation is. For instance, a fault can be modeled by using a transition, which ends in a state which is an error state. And from error state, what we can have some kind of failure transition where we can specify the failure that are originated in the output part of the component. Here, fault can also we can add information about faults which are originated from failures arriving at the input part of the component, as in this case. So this is an error model for the controller block, controller component, which has some input and output part. Here, for this kind of fault, named internal propagation, I can specify that this occurs when I have some specific fault at the input parts of the components. Okay, this is just an example to introduce the error model state machine. Here is the list of the entities that I can use in the error model state machine. So I have initial state representing the LT state. Then I have error states. Faults originated by the internal of the component that are modeled by using transition, and faults that are originated by external fault, which can be modeled by a transition stereotyped with internal propagation, as we have seen in the previous example. And then I can model failures by using, again, stereotyped UML transition, and where I can also provide, as we have seen the example, information about the which failures model are manifested in the component parts. Okay, the chess dependability profile also covers information about timing probabilistic values that can be attached to some of these entities. Okay, but this is not the focus here. So these values basically can be used to perform some stochastic based analysis, and can be used for this goal. But now focus on the information that are useful here in order to then allow the integration with the XSAP tool. So let me switch to a short demo about this. Okay, so let's suppose that we finished the modeling of the nominal behavior for our power system. Now I can create an error model for it, for this block, for this component. So I create a state machine diagram. Let me just name it in this way. Then I have to, here in the profile tab, I have to specify that this is not a standard state machine, but it is actually it is an error model. Okay. Here I can just focus on the palette which comes with the chess, which provides me with the entities that are defined in the dependability profile. So here I want to model the fact that the power system can fail, and in particular when the fail occurs, the component is not more able to manage the switching between the primary and the backup battery. So let me just create an error state for that. So I can call it stack at primary, for instance, and let's suppose that this error comes from an internal fault. Okay, and what I can say here I have an error because it requires some probability to be expressed, but in this case I can just put 1 because I'm interested in to analyze this as a kind of fault injection. So I want this as to happen with for sure, I would say. And okay, and then what I want, what I can provide is the information about the fact that how this error state can affect the nominal behavior. So let me just switch to the sorry. To another. Okay, let me use this now. And so this are the information that can be used here to then later properly feed the full tree analysis with XSAP. So here I can use some predefined effect that an error state can have on the nominal behavior, I would say. I can use the stacked action, which defines the property of component affected by an error. So together with the value, which is assumed by the property after the error. I can have the stacked fixed behavior, so affecting the nominal behavior, which defines the property of the component affected by the stacked fixed error. I have inverted for representing inverted error, and the ramp down. So here for the, which is quite, I can for the goal of this exercise here, I want to model the fact that in this error state, my power system is not able to switch to the backup battery. So here I attach to this error state a stacked stereotype, through which I can specify the property that is affected by this error, the property of the component, for which I am providing the error model. So in this case, I am providing error model for the power system, and the error affect here the state property, and the value here, which for this property in this after this error will be stuck at the primary value. Okay, so this is in this way I have modeled my effect on the nominal behavior. So I can provide, of course, this kind of information also for the other components. For instance, I can briefly show you the for the battery, which is controlled by the power system. So here I have a nominal behavior for the battery, which is basically very simple, just one state where the energy of the battery is computed according to the fact if the battery is currently powering the LED, or it is in the recharge, or it is recharging by using the generator. And then I have an error model here for the battery, where basically again I have modeled an error state due to an internal fault. And attached to this error state, again, I have provided information about the effect on the nominal behavior. Again, I have here a stacked effect where basically the energy of the battery is 0, so the battery goes down. Okay, so let me continue the presentation from here. Okay, so what I have shown is a way to model error for fault behavior by using dedicated state machine. In chess, we have also other possibility to provide the information about fault behavior by using predefined stereotypes, which basically have attached some kind of predefined error model state machine. For instance, we have the possibility to specify the fault behavior by using the simple stochastic behavior, which has some properties, and this is especially used for state-based analysis. In fact, it comes with the probabilistic and timing properties regarding the occurrence of the failures. And another possibility is to use this FLA behavior, which can attach it to the component, and through which it can be possible to use a specific dedicated formulas to provide the information about how failures can propagate from input to output ports. Here you can see an example of this specification, which follows the given syntax. We have support for this in chess for the editing of these expressions. And then in chess, we also support in order to use this information to perform a failure logic analysis. All of this information that are presented here with the stereotypes can also be modeled with the error model state machine, so all the information can be consistent between the two approaches. So you can retrieve the same information. And regarding failure logic analysis, you can check the work package for training section number 1, where you can find example of failure logic analysis that comes with the chess. Okay, it's all for me for this part.
Thank you, Stefano. Now it's time for all FPK people. So, change role to present. Okay.
Hello to everybody. Okay, in this slot, we present the integration between chess and the V&V tools. In particular, here, Okra and Reusable. This is the scenario of high-level scenario. The user edit, design a model, component model or behavior model, and properties, and he want to perform some kind of checks of the model, for example, contra refinement or behavior models against some properties. So it calls the external tools and then get the result and present the result to the user. In order to perform this, we have a tool adapter which expose a well-defined API to the model editor. And in order to hide the interoperability and communication technology that are used to interoperate with the tools. In addition, the tool adapter performs translation of the models of chess to the specific model of Okra and Luxembourg. The same thing for the result that are coming from the tools are converted in a format which can be shown by the editor. At the current time, in this prototype, we have two different ways to interoperate with our tools, by files and by OSLC. By file means that the tool adapter translate the models and write some files which are file compliant with the Okra in this example, and prepare a command file which appoint a link to the file, the model file, and which some commands that are related to the function that the user has chosen in the editor. Then run locally to the AMASS platform, the tool, and then get the result. In this case, is an XML file, and then present the file, the content of the file to chess. The second type is OSLC. In the case, the tool is running remotely, and we use the OSLC specification in order to interoperate with the tools. The tool adapter again translates the model, then invokes the consumer, which performs some kind of request, the web request to the server, and then get the result, and again present the result to the tool. It's important to say that for chess, it's totally transparent. The mechanism we are using to delegate, to communicate with the tool. It can be file or SLC, but for chess, it's totally transparent. The only thing to do is to configure in chess this kind of communication. So the demo. In the demo, we will see how to configure the protocol. So we go on Windows preferences. Here, model checking tools. This form is composed of two parts. The first part is related to the case of file. So we specify the workspace dir where the tools can store some files, intermediate files. Then we set the Okra executable here, looking in the file system, and then test. We can see if the installation is correct and the version of the tool, and we can set the timeout in second for each invocation. For Luxembourg, the same. We have also here okay, we found the version, and then the timeout that can be different, obviously, from Okra. The second part is related to the OSLC. So here we have the URL of the web server where is running the service catalog. The service catalog is a catalog where I store the address of the service provider OSLC. So we have here is an internal internal server. Clicking on Show Service Catalog, we see the list of services currently available on the server. At the current moment, there is only one, which is an automation OSLC domain, and this implements the API towards the tools. Okay, in order to enable via file or via OSLC, the only thing to do is to check the box here. Okay, the configuration is completed. Okay, And now, in the next presentation, yeah, we will see how to interact with the tools.
Okay, so now I'm showing how to validate the contracts. So at this stage of the workflow, for the user, it's important to check if the contract that he has created are the contracts that he has in mind. So to do this, there are three kind of validations. The first one is the consistency. So in this case, with this kind of validation, basically it's possible to check if there are no contradictions among a set of properties. And these properties can be assumptions or guarantees of contracts. So, and this schema shows which are the inputs and the outputs of this check. So in inputs, there are this set of properties that the user has to choose, and the output depends on the result. So if there are no contradiction among the properties, so if that it means that the properties are consistent, there is a message that says that the check is okay, and also a trace is shown. Otherwise, there is only a message that says that the check is not okay. And this is the first type of validation. The second type is called possibility. So, and it is similar to the previous one, but in this case, there is another input. So here the user edit an expression, and we want to check if this expression plus plus a subset of properties that also in this case can be assumption or guarantees of contracts are consistent with each other. And again, the output is the same. So if the check is okay, a trace is shown. Otherwise, there is only a message. Then there is the last type of validation that is called assertion. And in this case, we want to check if all the possible traces satisfies the set of assumptions that the user has selected. I mean, if it satisfies the expression that he edited, that is entailed by the set of assumptions and guarantees that he selected. And in this case, if the check is okay, the tool returns only a message. Otherwise, it is shown a counterexample trace that basically proves that there is a violation on the property. So now I'm going to show how the user can validate the contract in the AMASS tool, so in chess. So this is the WBS, the wheel braking system example that was used also in the previous WP3 section. So here basically we select the system component. We go to chess validation, check validation property on selected component. And here Okra wants to know if the time model of the project is discrete or hybrid. In this case, it's discrete, so we select discrete. And here there is a pop-up. So first of all, we select the consistency type. So as you remember, with this kind of validation, we needed to put in input a set of properties. So here we select a component, in this case the BSCU, and here there is a list of properties that are composed by the assumption and the guarantees of the contracts associated to this component, plus the assumptions and guarantees of contracts associated to its subcomponents. And here the user can select one or more of those properties. And then it clicks on OK. So here what happened? So first of all, here there is a V&V results view. And in this view, it's possible to see all the commands that are executed in this section. So in this case, as you can see, there are two commands, and for each command it's possible to see the type of command, the status, so if it's completed or not, the date, the duration, and the result, and also the user. And so we can select one command and see the result. So in this case, another view is open, that is the validation property trace. And here is possible to see the result of this validation. So in this case, there is the message that tells us that the check is okay. And we have also a trace. So selecting the trace is possible to see for each parts of each component, it's possible to see the value of each part for each step. And here you can see there are some cells that are colored in red. It means that the value of the part is changed with respect to the previous step. So for example, we have the part CMD_AS of the component BSCU1 that at the step 1 is false and at the step 2 is true. Okay, so this is an example of the first validation check. Let's see also the other two. So again, we select the common validation property. We select the second check. We select the component. And now the difference is that the user has to insert also one expression. So in this case, we can insert a simple expression. Always pedal pose 1. Pedal pose 1 is a part of the component BSCU. And again, the user can select a subset of the properties that are in this field. And again, in the V&V result view, it's possible to see the status of this operation. And in the validation trace, it's possible to see in detail the result of this current operation. Again, we have a message and the trace. Now let's see the last type of validation, that is the entailment. Again, we can write the same expression. Let's see what happens. So here we have an error because there is a trace that violates the property, and this is the trace. So it's possible to select the trace and see in particular what is the specific trace that violates the property that we have defined. So that's it basically for the contract validation. So at this stage of the workflow, it's also possible to perform some verification. And in particular, now I'm talking about the check of the contract refinement. So in this case, the check of contract refinement means that basically the following properties must be valid. So first of all, we have to check that the properties that are related to the composite component has to be valid. In particular, that the contract of the composite component, so the assumption and guarantee, must follow from the contract of the subcomponent. And here you can see an example. And the other set of properties, that must be valid are related to the subcomponent. In particular, it's important that the assumption of each subcomponent must follow from the contract of the other subcomponents, plus the assumption of the composite component. And here you can see this property formally written. So here in this scheme, it's possible to see which are the output of this check. So it takes in input the information about the contract refinement that, as you remember, we talked about it in the previous session. And as output, it returns a message of OK if everything goes well. Otherwise, it returns one or more counterexample traces. And now I'm going to show you in chess how to perform the check of the contract refinement. So again, we select the system component. We go to chess, functional verification, check contract refinement on selected component. We select the discrete time. And here we can see again what happened in the V&V result view. So we see that there is a OCRA check refinement completed. And we can see also the result. So let's see, first of all, how many contract refinements we have defined in the model. So if we go to the contract refinement view, it's possible to see how each contract defined in the model is refined. So here we have 3 contracts that are refined, okay? And here it's possible to see the result of the check of those 3 contract refinements. It's possible to see that 2 of the 3 contract refinements are okay, but there is one refinement that is not okay. And here it's possible to see the counterexample traces. So here there is an error because I intentionally made a mistake in one contract. So if we select this contract, the break contract, and here we modify the assume property. Now we can try to perform again the check refinement, check control refinement, and see what happens. We can also try to change the way we interact with the V&V tools. So now we are invoking the V&V tool locally, but we can try the OSLC service to see what happens. See what happens when we invoke a V&V tool using the OSLC. So again, we select the component, we go to chess, functional verification, check control refinement, we select the discrete time. And as you can see, from the user point of view, the mechanism is transparent, so is not, the user doesn't perceive the difference. And here is possible to see the result. So in this case, all the three control requirements are okay, because I modified the assumption of the contract system break time. Okay, so that's it for this slot from my side.
Okay, thank you, Alberto. Okay, let's move to MDH. Irfan.
Yes, thank you.
To presenter. Okay.
Okay. Can you see my screen?
No, right now no, it's empty. It seems loading now.
Yes.
Okay. Yes, right
Okay.
now it come up.
Okay, I have a quick presentation and then I will demo the stuff. Okay, let's see. So I'll just do a little bit of. It's good that I'm after Alberto because he introduced the basics there. I will see how to deal with the strong and weak contracts here. Though we used here legacy support for the refinement check, but I guess it could be synchronized later on. I'll use a bit different system. We don't need to go into details, but let's say we have a simple composite component consisting of three subcomponents. It's this lifting arm, automatic positioning, loading arm controller unit system for these wheel loaders. It's essentially a controller that moves the these arms up and down. It has one reusable component that we find interesting from the weak and strong contracts perspective. This automatic arm positioning, it behaves differently in different contexts, in different loading arms. Whether the loading arm can go very fast, so these are some hazards in the system. Unintended movement of the arm or movement of the arm during high speed and so on. And in all the different cases, this lifting arm component can contribute to these hazards. But it behaves differently if the vehicle is capable of high speed, or if the vehicle has a predefined position in which the arm is automatically moved, or this position can be set by the user, by the operator, and so on. So there are some variable behaviors. And if we look at what Alberto was presenting just before, if we want to do the refinements in contract-based design there, then we will define a contract on this composite level, and then we'd have contracts on the subcomponent level, and we want to check this refinement that it works. But when we look at this component, this automatic positioning component, it's a reusable component, which means that we have defined a set of contracts for the same thing that talk about different environments, so different settings. If the vehicle is capable of high speed, so the environment of this component, or if it supports this automatic positioning, or if it supports fixed automatic positioning or dynamic and so on. So there are different cases how this component behaves corresponding to how the environment is actually. So to check, this is when we use these strong and weak contracts, actually the weak contracts, because then we can describe these variable behaviors on the contract level, the behaviors of this component in different environments. We can describe them by weak contracts. This essentially means that those contracts are not required to be satisfied in all those different systems in the same system. But for example, if this component is used in a system that doesn't support high speed, then for example the second contract is only relevant there. The others are not cannot be validated in that environment. If it's some other wheel loader, then perhaps the first one is used and not the others, and so on. So to check actually refinement here, we first need to check the validity of these weak contracts, select the ones that are appropriate, and then do the refinement check. So OCRA doesn't explicitly support these strong and weak contracts, but we have the possibility to model them in chess. So we were just looking here how we can actually automatically select which weak contracts should be included, for example, in the refinement checks and so on. Or can we do, if we don't know which contract to select, can we check the refinement with all the weak contracts, and how to do it for the refinement doesn't fail. So I'll go briefly through an example here. So just without going into details of this very system, let's say we have this composite component with one particular contract specified on fault propagation, and we have 3 subcomponents. Each of them has some contracts, and this is this reusable component, which has a set of weak contracts describing the behavior of this component in different environments. So those different environments are, let's say, from the perspective of this component, they are defined by these parameters. For example, what is the maximum ground speed of the vehicle? What is the ground speed limit? So these 2 parameters tell us if the vehicle is capable of going high speed or not. If this automatic positioning is static or dynamic, that is, if the position in which the arm will be automatically located or moved, if that position is predefined, or so that's the default position, or if it's possible that the user sets it. So those are all some variations from different wheel loader products. And this would be an internal diagram how it essentially looks like. The composite component, 3 subcomponents, and this is this automatic positioning. And this is where we set these parameters that I talked about that define for this component instance of this reusable component, that define, okay, its weak contracts. So when we have it like this, if we check the contracts here, then we have this a set of contracts, and we need to see a set of the weak contracts. We need to see which of those is applicable in this particular setting. So what we can do is here in the analysis part, if we make this contract refinement analysis context, and we set that we want to check these weak contracts, then we can use this legacy support for this, and that will essentially perform the command that Albert was presenting on consistency of the weak contracts, and it will give us the results in a pop-up. Now we want to continue. It will give us the results, and it will automatically update the status of the contracts, but also it will automatically select the appropriate weak contracts in the component instance model. Okay, so let's see. because once this is done, then we actually know. So here, for example, so it will tell us. So as Alberto was saying, the outputs for the different weak contracts, for example, it will tell us if it's okay or not okay, and it will give us this also trace here. But so we don't care at this point that much about the details here. That can be done in other way. But once we click OK, then this should, if we go to the internal block diagram for this particular component, and we go to properties here, and we'll see that this particular contract, weak contract, has been selected as the one that is supposed to be checked, and the one that is validated in this particular environment. So the same thing is if we go to the block diagram, it will be updated here as well. Unlike the others. So then, if we want to check the refinement, for example, if we select all these contracts that we want to check refinement against this one, then the refinement, standard refinement will fail because not all of them do refine this in this particular environment. But what we can also do here, there's another possibility. If this is still set to true, then we can check refinement with all of these contracts, which will essentially first transform these weak contracts into an implication, guaranteed sort of implications. So there are details about this in the deliverables, which then can be checked for refinement against the top contract, and it will tell us if any of the contracts can support the refinement or not. And then, so here we have the checking against all the weak contracts, which means that at least one of those weak contracts can support individually the refinement check. And then we have established that that one is the first one that can do that. So if we go to this one, and actually here when we're doing specifying which contract refinement should be checked, we can actually check here that it's only the first one, and then if we do the refinement check standard way, so to say, without setting here to check all the contracts, then it will, with this particular weak contract, the standard refinement will also be done. So this was the part on checking the strong weak contracts and selecting them automatically. Later on, we'll see the rest on the assurance side. That will be all from my side for now.
Thank you, Ivan. Next thing is the question slot. Do you have any questions regarding these topics? Okay. No questions? Okay, so we move to the next main topic, which is safety analysis. Now it's time of Marco.
Can you pass the ball to Alberto, please? Because we share the same computer. Okay, so I just have a couple of slides to introduce the XSAP tool, and then Stefano will present for the analysis using XSAP. So XSAP is a platform for model-based safety assessment for critical systems. It has been developed by FPK. It has a long history, so the development began in 2002. There was a previous version called XSAP. The latest version has been released last year, and so it enables the main concepts of XSAP are the separation of the nominal modeling and the modeling of faults, so what is called automatic model extension. So this will be illustrated in the demo, in the presentation by Stefano. And in addition to faulty analysis, there are also a lot of other analysis that can be done. The license of XSAP is free for non-commercial applications and also for academic purposes, and you can find additional information on the website. And in summary, this is the workflow of XSAP. So you can see on the left-hand side that it's possible to model the nominal behavior of the system and to specify the faults using taking the specification of the faults from a fault library and by giving some fault extension instructions. By taking these inputs, the system can automatically extend the model by incorporating the definition of faults, and you get an extended model, and you can use the extended model to generate a lot of artifacts. So for trees, but also FMEA tables, it's also possible to do common cause analysis, probabilistic evaluation, and so on and so forth. So I will now give the presentation to Stefano. So you have to pass the ball to Stefano Puri, I believe.
Okay, I can help you. Stefano here, presenter.
Yes, thank you. So let me share my screen. And just follow the presentation. So thank you for the introduction of XSAP. So what I'm going to show you now is how it's possible to use the information that I have shown before regarding the nominal and faulty behavior of the components in order to generate, in order to apply faulty analysis with the XSAP tool. So just to recall what we have done, so we have modeled the architecture, the component architecture with the component input, output, and port, and the composition made by internals and connection between them. And then we have provided functional nominal behavior by using state machine, and error model behavior by using a dedicated state machine. We have provided some failure effects regarding the error states of the component by using predefined the library of possible failure modes that can have some effect on the nominal behavior. So next, the next step is to create an analysis context, so a specific entity which can be used then to collect the information to run the analysis, in particular the top level component that has to be considered for the analysis as a root entity. And then we have to provide the top level condition, Boolean condition that to check for tree analysis. So let me switch to the demo in order to show you how the analysis context can be modeled. So again, here I have my model of the battery system that I have used before in order to introduce the modeling of the nominal and error models. Now I have in order to provide the information about the analysis context, I have to move to this analysis view package, in particular under the dependability analysis view. I can create a new diagram. So a new diagram, for instance, class diagram. Okay, here I have a list of possible analysis context currently supported in chess. So we have already seen the contract file analysis from the demo made by Irfan. Okay, we have this one which is related to the state-based analysis, which is supported in chess and uses the probabilistic information that I was referring before. That is possible to attach to the error model. And we have also the failure propagation analysis also presented briefly before in the, while presenting the error model. And then we have the possibility to specify analysis context for FTA with XSAP. I can provide a name for it. Okay, what do I have to provide for the analysis context is a couple of information that are available under the profile tab. So this analysis context comes with predefined property. One property that needs to be specified is the root component, as I was saying, and so in particular, in order to specify it, I have to tag the root component by using a dedicated stereotype. So I have to select my component, which I want to use as root. And here in the profile tab, I have to click on the plus button and select this GHGA resource platform stereotype. Okay, now I can come back to the analysis context, and I can use I'm now able to refer the block I've just stereotyped in the platform attribute of the analysis context. So here I can see my battery system that I want to use as root. Then I have to provide a condition for three analyses. Basically, for this demo, what I want to check is a condition upon a property of the LED, which is a block which is powered by the battery, which has a light property, which is a Boolean condition. So a light basically means that the LED can emit light when the energy provided by the battery, the primary or backup battery is greater or equal to the load or associated to the LED. So this is the Boolean condition that I want to check. I can specify this condition here in the analysis context, again under the profile tab. Context, I can in the context attribute I can add this condition. So I want to check in which cases I can have that the light of LED can be false. So my LED is not it does not have light. I can save. Now I have specified all the information, so I can that is needed in order to perform the analysis. So I can now proceed with the invocation of XSAP tool, which has to be previously set as presented before during the setting of the FBK tools. So here I have to go to analysis, dependability, and FTA with XSAP. And here I have to select the analysis context to be considered for the run of this analysis. In this case, I can I have only one analysis context, the one I have just created. Here I select analysis context, and this here in these fields below, the properties that I have specified for the analysis context are summarized again. I can proceed, so I click OK. And so the tool automatically performs some steps. So it generates the SMBV models starting from the definition of the architecture, definition of the nominal behavior, and definition and generates the extended model considering the modeled fault behavior, and then invokes XSAP, and XSAP performs the analysis and compute the fault tree. Currently, the fault tree is showed automatically by using an external viewer, but we are working on different support, which foreseen the usage of an internal viewer for the fault tree. So let me just zoom in order to. Okay, so the top level event is the one I have specified through the analysis context, so let the light faults. Here I can show. Okay, I have some delay with the. Okay, maybe you can already read. Maybe with the some. Okay, if you read these are the minimal cut event that can lead to the to this condition. So let's equal false. Basically, here we can retrieve basically the error states that have been defined in the error model. So, for instance, I can have this condition when my power system is in a stacked primary error. If you remember, this is an error state that I've put in the error model state machine. And other possibility are that I can also lead to the condition of let light false when one of my battery enter the error state energy stacked 0. If you remember, this is another error. This is the error that have been specified for the error model of the battery. So here we have the condition for the backup battery and for the primary battery. So this is basically the how the analysis run and the information that can be showed according to the in the fault tree according to what has been provided in the model. Okay, so that's all from my side regarding automatic fault tree generation with XSAP. So I can move. We can move to the next presentation.
Thank you, Stefano. So we are coming back to FVK. No? Yes. FVK presenter. Yes. Okay, now Stefan, sorry, Alberto, document generation.
Can you hear me? Okay. So now I'm going to talk about the contract-based safety analysis that is different from the model-based safety analysis that we previously see. So in this case, it's OCRA that performs this kind of analysis, and it takes in input the information about the contract refinement. And as output, we have a hierarchical fault tree, like in this example, where basically the top level events represent the failure of the system implementation in satisfying the contract that is refined. And then the other nodes of the tree may represent the failure of the system environment, like in this case, satisfying the assumption of the contract that is refined, or the nodes may represent the failure of the leaf components in satisfying their contracts. And so this is just an example of fault tree that was automatically generated with Okra. And now I'm going to show you how to perform this kind of analysis in chess. So let's return to the wheel braking system model. Again, to perform this analysis, we have to select the system component in this case, because we want to generate the fault tree starting from the contract associated to this component. So we go to chess, safety analysis, safety analysis, contract-based safety analysis on selected component. Okay, now Okra is working. We have to wait 10 seconds, more or less. And so now the file that represents the fault tree is created. And here you can see an editor where it's possible to see the result of the analysis. So this is the fault tree that is generated. And selecting one node of the tree is possible to see what is the failure that this node represents. Exactly as I show you in the slide. So this file, this fault tree, all the information about this fault tree is stored in this file, that is the representation.ird. And this file is created every time we perform a contract-based safety analysis. And with this editor, it's possible to zoom in, zoom out, and also move and rearrange the position of the nodes. It's also possible to export this diagram as image if the user wants. So that's it for this specific safety analysis from my side. And if you have a question about the safety analysis, now it's time to ask. Otherwise, we can move to the next slot.
Okay, no more questions? No? Okay, so we're going to move to safety case. This time is by Irfan. So I make him presenter. Okay, perfect. And now I mute. So I mute you.
Can you hear me?
Yes. Yes.
Great. Okay, just a few slides on the topic. Okay, so if you remember what we did before, we have these contracts on the composite component and the subcomponents. Now what we were doing is so what we initially want to use this for, the contract structures, is to validate that certain requirements on our system are met through these contracts. By checking the contracts, we can see that the requirements are achieved in the system, in the model. So what we're doing here, if we want to assure that really a particular requirement is satisfied, then we need some confidence that, for example, the contract correctly formalizes the requirement, that we have confidence in the contract itself, that it represents the reality, it represents the code and so on, the actual component implementation and so on. So what we did here in chess, we extended and allowed the possibility to enrich the contracts, not the contracts themselves, but information around the contracts with some assurance information or information needed for assurance. So what we can now establish relations between, of course, requirements and contracts, which was all possible before. We have possibility to connect assurance artifacts such as evidence, like testing results or whatever we have in our assurance case with the contract. Also context statements, which are essentially informal descriptions of the formal contracts, because the contract language itself is not readable by everyone. Not everyone talks formal LTL, for example, language. So whoever wrote the contract should make sure to also have informal explanation of that contract so that it can be used in assurance. And then, of course, traceability between these contracts and the argumentation or assurance that we have created corresponding to them. So this is essentially one pattern of assurance and how and what actually it tells us what we need to assure if we want to show, for example, that a particular requirement in our system is satisfied with sufficient confidence. Then we need to show that the requirement, if we want to do that via contracts, we should show that the requirement is correctly implemented or formalized by the contract, the corresponding contract. And then we need to communicate confidence in that contract, meaning that the implementation of that contract actually behaves like that, for example. So to do that, we have this part of contract is satisfied with sufficient confidence. On one side, we should make sure that the refinement check has passed, meaning that the subcomponent, eventual subcomponents of this particular component or subcontracts are correctly refining that particular contract so that all checks have passed. We should make sure that also the assumptions on the environment of that contract have been met. And then we can add some evidence regarding its completeness, and this relates directly to the implementation, how that actually the implementation behaves. So this is an argumentation pattern on assurance, for assurance based on contracts, and it just tells us connections that we need to have to be able to assure something, to be able to, for example, assure that the requirement is satisfied by using contracts. So if we go now to the back to this example here, we can have a set of requirements. If you remember that system on a loading arm, automatic positioning of these wheel loaders, loading arms movement. So there are some requirements such as the stop position of the arm shall not deviate more than this much, or for example, positioning shall not start on its own, that is without user initiation. The arm position shall be disabled during high speed and so on. And we want to show that through the contract, some of these are met. So if we have these contracts that are talking about, for example, the accuracy and that are talking about high speed, these requirements, the arm shall not start without user initiation and so on. So then in the contracts, when we're specifying contracts for the top level, we can here, if we go to the contract and if we go to the profile of the contract, we can see here, okay, the assumption guarantees, and we can see the connection to the particular requirement this contract is formalizing. We can also see the type of the contract, that is language, and a sort of informal description of what does the contract represent, actually. So in this case, so we have several different contracts and all of them can be described. What we can also do, we can associate some artifacts there, but there was still an issue with connection of this kappa connection to do the connection of this with artifacts. But we can see the connection on the assurance side. So how to generate actually and propagate this information in the assurance side? We are now in the OpenCert preview, and what we need to do is this is being generated directly in the what is this problem? Okay, it doesn't allow us. Anyway, what must be in existing directory? Okay, let's just look. So if we go to OpenCert, what is needed here is that we have specified the repository preferences, because the argumentation that we're generating is being generated directly on the repository. So here I'm using the localhost one, but there are others that you can use wherever you have your repository or CDO repository. So here we have the connection to this repository, and there are a set of projects, assurance projects, and we will be generating to this particular one. So how to do that is, if you go to this analysis that we talked about before, or not necessarily analysis, you can generate it actually from anywhere. You go to chess, argumentation, generate argument fragments. It will ask you to select the analysis context, so we know the system and so on. And then it will ask you to select which project you want to generate the argumentation. So what this will do now, it will start generating argument fragments or diagrams, modules for each of the components in the system. It will be using the information about the contracts of each component, and in particular, if you have weak contracts that we talked about before, then it will be using only the weak contracts selected on the component instances, which means that it will be using only those that are relevant, that are selected to be relevant for this particular system. And then it will also present this in argument structures. It will present the contract refinement connections also between different modules for different components. What this does also automatically, it automatically traces each contract that we have defined in our model with the corresponding claims in the argumentation side. So we can see that now. Okay, it's generating. Okay, we have generated fragments, so we should, if I select the right one, right? Oh, I selected this one. So here are the generated arguments. If we open one, so this is, for example, information that we got from this side. This is this propagation contract and the connection done. So it's not very beautiful on the first go. So you will have to by yourself go around and check a little bit and expand things and see. But you have everything written here also. So if we go on this side and we, for example, where we have these OpenCert tabs, we should have them on this level, I think. Not here. Is it here? No. here either. For example, here we should have an open search tab, not even here either. Yeah, so here it will tell us. So actually I selected this particular one. So this component, for example, is traced to this argumentation element, and if we go, so I selected the wrong one. Let's see, I selected this one. Yeah. So here we can see I generated argument here. So it goes, for example, this one. It's traced to this component. This element is traced to this component, and this is captured here in this Capra traces. So these traces are saved. This particular directory is automatically created in the in your Project Explorer, and this one saves these traces here. So if you delete this repository, all the traces that are captured between elements here and elements in these diagrams will be also deleted. So this was from my side everything.
Okay, thank you, Irfan. Now it's time to go back to Stefano. Here. No.
Yes, thank you.
Okay, great.
So let's continue. So let me just continue with what has been introduced by Irfan. So regarding the possible links that can be specified between the architecture entities and the assurance project ones, in particular claim and evidences. So we have started to define this possible association in the AMASS component meta model, and we have provided support for this in chess and in the OpenCert platform by using a dedicated tool supporting for traceability. This is basically this slide summarizes the entity in the architecture that can have a corresponding entity in the assurance project. So the entity at the architectural level, so in chess, are the formal property, contract, analysis, contest, and block. And so we have already seen, thanks to the example provided by Irfan, an example about association of a block to the corresponding argumentation element in the argumentation model. Then we can have also other kind of traceability links that can be created by using the already showed OpenCert tab, which is can be available by using the chess Papyrus editor and by selecting one of these entities. So in particular, so for instance, for the formal properties, which I recall represent a formalization requirement, you can specify claims that are defined in an assurance case. For instance, you can claim about the formalization of a given requirement, and it's possible to link to the corresponding formal property in the chess model, which formalizes that requirement. And then for contract, it's possible to have links to claim. For instance, it's possible to provide some argument about how the contract, for instance, has been derived. For instance, we can have contracts derived from some of failure analysis and some from some safety requirements, or you can argument about the specification of the contract itself. When we can have a link to an agreement in the assurance case, with this part regard to the fact that in the assurance case we have to give some reasoning about how the assumption of the contract is fulfilled by the environment where the contract, or better the block owning the contract has been instantiated. And then we can have a link between contract and artifacts. The artifacts basically can be used to provide evidences about contract validation. So, for instance, you can have some kind of test of simulation supporting the contract validation, and this kind of artifact can be stored in the OpenCert artifact model, and then retrieve and then link it to the contract by using this association. Then we have for analysis context that we have already seen in, for instance, previously for contract refinement or also false regeneration. It is possible to have a link between analysis context and the artifact. So basically the analysis context is used to provide to run a particular instance of analysis. This analysis produces some results, some artifact that can be referred by the artifact model in the OpenCert project, and also this kind of artifacts can be related to the analysis context in order to be able to retrieve later the information that have been used to produce that particular artifact. Yes, as already said by Irfan, so these kind of links for traceability are currently stored in dedicated meta model, which is created and managed automatically. So let me just show you briefly a demo about this. So we have already seen something about it in the presentation made by Irfan. Let me just show you once again the usage of this OpenCert tab. So let's think, for instance, to have. So this is the repository shared, so available with in the repository Explorer OpenCert tab, where you can create assurance projects. For instance, here I have created a very simple, I would say, toy example of assurance project that have an argumentation diagram, which basically is just a simplification of the pattern that have been introduced by Irfan. So this is just for the sake of this demo. So this is an argument, an assurance case, which elaborates on the specification of a contract which has been provided by as a formalization of the given requirement. Maybe you can recall the break delay requirements that have been addressed for the will break system example during the previous session. So here we can elaborate on the fact that the contract has been properly formalized, and that the fact that we have some contract refinement, that the refinement is correct, and here we can produce some evidence related to the contract refinement analysis. For instance, let me just focus on this. So this goal, which tells about that the requirement break delay of our will breaking system example as is currently formalized. As you probably can remember, in chess we have the concept of formal property, which can be used to formalize the requirement. So what we can do here is to show how a link between this formal property and this claim can be created. So so by using the feature already presented by Irfan, some of these links will be automatically created. I just here I just show you some example about the usage of this traceability support that can be used in order to further refinement this traceability information between the architecture and the assurance case. So in order to link these two entities, here I have to I have to select the formal property here, and by selecting the formal property here, you can see a tab OpenCert, which shows the claims currently attached to the formal property. Now there is no claims attached to this formal property, so I can do a link now. In order to link the claim, I have to currently I have to use another way to retrieve the claim to be linked. So I cannot use the OpenCert repository explorer view, but I have to use the CDO transactional checkout, which can be created in the project explorer. Let me show you how this can be created. So you have to first of all show the CDO repository view, which can be shown here by using show view other, and by selecting here under CDO repository. Then you have to create a new repository, for instance, by connecting it to an existing remote repository, like the one provided in AMASS. And here you can provide all the information that that refer to the shared remote repository. Once you have provided this remote repository, you can right-click it and select checkout. Okay, this creates a transactional checkout here, which loads all the information that is available in the remote repository, as they are showed here in the repository explorer tab. So here you will retrieve the exact information that is showing the repository explorer tab. So here I can navigate the information. So I can just go to my test assurance project, and I can navigate, for instance, the argument model. Indeed, I want to link my claim regarding requirement formalization to my formal property. Now I identified my claim here. Then again, you have to select the formal property, go to the properties tab. You have to pin the property tab in order to make it fixed in the properties view. Then you can select the claim and from the project explorer and drag and drop it on here on the OpenCert tab. By doing this, the trace link is automatically created. It's automatically created in the current workspace trace model, which is automatically managed. You can have some initial support for navigability. So for instance, you can here double-click the claim associated to the formal property, and the corresponding so the claim defined in the argumentation model is highlighted retrieved and highlighted in the project explorer. So this is just a way to navigate the information that is linked. Okay, so and this the support for as I was saying, for this OpenCert tab, you can find it for the other entity that I have introduced in the slide. So you can here again you can use the same mechanism in order to perform the traceability between the architectural entity and the in this case assurance case 1. So that's all basically for my slot regarding the traceability links. Thank you.
Thank you. And now let's move to Alberto again.
Okay, can you see my screen?
Yes.
Okay. So now I'm going to talk about the document generation. And this activity is very important, especially if the user wants to certify the system. So with in CES, it's possible to automatically generate document in HTML format, and this the document that will be generated will include different information. So we'll include information about the components of the system, the parts, the attributes, and the contracts, and the format properties. Not only textual information will be exported, but also diagrams that will be exported as images. And we plan also to export the results, the outputs of the analysis that we have mentioned in this session. So the verification, the validation, and the safety analysis. So now I'm going to show you how to automatically generate documentation in CES, so in the AMASS P1 tool. So again, we are in the wheel braking system model. All we have to do is to select the system component, go to CES, safety case, document generation, and click on generate documentation from selected component. Here we have to select the output, the directory. So we create a new folder. And here we have to choose the document format. Now it's only available the format HTML. And here there are some options that we can choose that are related to the generation of diagrams. Okay, we click on OK. And okay, now the documentation is generated. So we go to the folder. So here you can see the HTML document and also the images that represent the diagrams of the system. So if we open the document, it's possible to see first of all the block definition diagram, and here we have a panel where it's possible to navigate a specific component of the system. So if, for example, if we select the system, it's possible to see the internal block diagram of the system, and there is also a table. There are numbers of tables, so it's possible to see which are the input part of the components, the output parts with the respective type, which are the subcomponents, and the connection, and also it's possible to see the contracts associated to each component. So basically, this is the all about the automatic generation feature. So, and as I mentioned before, we plan to include additional information related to the validation, verification, and analysis of CES inside this document. So about the safety case session, I have concluded my my part. So now it's time to questions, if there are.
Questions there? Okay, seems that there are no questions. Okay, anyway, you can ask later by email or just via myself, but anyway, you can ask later if you find out some questions when you are dealing about this topic. Okay? So thank you, Alberto. Okay? So we move to the next section, which is upcoming features. This will be a collection of features that will come up in the next prototype, but now some of the partners can show us a preview of their work about these topics. First one is Savona. It's going to be Marcos Grabowski from Bernard and Marner. So change the role to presenter to him.
Yep, thanks. So, okay, just wait a second. I think I've shared the wrong monitor. Okay, so, okay, can you see my screen now?
Yes.
Okay, great. So I'm going to give a very quick overview on Savona. With Savona, we are trying to create a clean and easy way to design static system architectures and specify the system by using contracts. So what you can see here is basically the same internal block diagram offered by Papyrus, which is also used in within Chess. And I would like to explain Savona on this little airbag system example. So the airbag system has an import with the vehicle acceleration coming in, which signal is continuous. And as an output, there is also a continuous port which emits a current pulse that ignites the actual airbag unit. And within the airbag system, two redundant crash sensors are always watching the vehicle acceleration, and if a certain vehicle acceleration value is detected, then the crash sensor actually detects a crash and sends a Boolean signal to the airbag controller, which waits for each of these airbag crash detection signals to become true. And if these are true, an ignition command is sent as an event to the ignition unit, which is further then providing the current pulse as an output for the airbag system itself. So what we are doing here in Savona is to use semi-formal assertions for contract definition. And in these semi-formal assertions, we are using names from the system model to fill in our pattern language, such as the port names or values from our data dictionary, where the user can create enumerations, constants, or custom units. We also provide a set of predefined units which can be used in our patterns. So this is that, and what we are now going to do is create an assertion on the airbag system level here. So let's just hide the internals. So we've got just the import and output here, and we've got a constant here, crash detection bound, and what we are now going to express is an assertion which says that the vehicle acceleration must always be greater than this crash detection bound. Otherwise, the airbag system is not going to detect the crash in the right way. So what we can do now is go to the properties view of the airbag system, switch to the assertions tab, and add an assertion by using the assertion wizard. Within the assertion wizard, we guide the user through most of our pattern expressions step by step. So at the first step, the user needs to select a general pattern type. In this case, it would be the global invariant pattern types. To each of these types, there's an expression and an example for the user to understand and check which pattern might fit the most. So let's just select the global invariant patterns and hit next. And at the next page here, the user can select a more specified pattern for his expressions. The first pattern type here is sufficient for our expression we are going to formulate, so hit next. And now we can finalize the pattern by substituting actual model element names from our system model in the background. So what we are going to say is that the vehicle acceleration must always be greater than a specific value. So we would choose this one here and say that the vehicle acceleration is always, we can deselect certain pattern entities which are in those kind of brackets here. So as we want to say that is always greater or equal to some value, we choose greater or equal to, and the value is already defined in our data dictionary as a constant, so we choose constant as a value and find our predefined constant here. We click transform to get a quick summary or final overview of our assertion, which is to be defined, and that looks good so far. So let's hit finish there, and we can see that the first assertion is created on the airbag system here. A second assertion is now going to be defined. Actually, we are now going to define the reaction, which lets the airbag system ignite the airbag. So in such kind of way, or the requirement would be that whenever the vehicle acceleration decreases below a certain threshold, then the airbag shall send such an ignition pulse of some current within a certain deadline. And this time we are using the assertion editor, which is an Xtext editor, just as used within chess. And here we can also use the content assistant to provide possible ways to continue within our assertion. And here we can just type in our assertion, or let us help with the content assistant to formulate the right assertion. So the expression would be here: whenever the vehicle acceleration decreases below, let's say, -50 meters per square seconds, then in response, a current pulse enters the range from 1 ampere to 3 amps, and the deadline would be after at most 50 milliseconds, for example. So yeah, as the XS editor does not mark anything red here, the syntax is used correctly here, and we can hit OK. We now have those two assertions defined on our airbag system. So we can now use these both assertions on a contract or as a contract using the contracts tab here. We hit the add a new contract button here, give the contract a name, maybe airbag contract. We can set a description here and use our defined assertions either as an assumption or as a guarantee. And if those assertions are selected as assumption or as a guarantee, we can hit finish and see that a new contract is defined here. And what we can do now, if we specified all of our system components, so to save some time here, I've already specified the crash sensors, as you can see here, the airbag controller, and the ignition unit. So all of those components already have some contracts assigned. So we can do an export now to chess to do some V&V stuff. So export this model here. I've already prepared it due to time reasons. So let me just switch to the chess AMASS prototype here. So as you can see, it is the exactly same model here. And what the export does is actually turn all assertions to formal properties and turn all contracts to chess contracts and assign a contract property to the corresponding block. So if we select here on the airbag system level the contract property, we can see our assumption and guarantee, which we previously assigned within Savona, and can now manually translate these assertions into HRE LTL also on to validate these contracts with OCRA. This is the current status of the project. What we are planning to do is to automatically translate our semi-formal expressions to HRE RTL, for example, so that the manual translation within chess does not need to be done. Okay, that was it from my side.
Move to Honeywell people. I don't know which one I should change the presenting right, say that Thomas or Vit.
Please change it to Vit.
Okay. Okay, perfect. There you are.
Okay, thank you. So this presentation is about the V&V manager. And these main tasks are the ones which are the concern of this V&V manager tool. So validate requirements, verify state machines against those requirements, and generate reports which are say more about the results. This is some kind of high-level process which is necessary to run the V&V manager. Those steps which are contained in the green.
Sorry, we cannot see your screen.
Okay. Can you see it now, please?
Yes.
Is it better? Okay. Sorry for. So I have already said this out loud, so I won't repeat it. This, I'll make it larger. This is a high-level process which leads to the initiation of the V&V Manager tool. The steps which are bound in the green rectangle are out of the scope of the tool, but they are necessary. So we have to first define the blocks and formalize the requirements and capture them as contracts. And then the V&V manager is run from a block, and it collects the related formalized requirements and sends them to a remote verification server, which then does the validation and verification work and sends back the results, which are then highlighted or displayed by the V&V manager in the AMASS platform. So I will now switch. So here we have a block which contains or is described in 3 contracts. Each of the contract is bound or formalizes requirements captured here. So we can see the informal text, and this is then formalized in a more readable form and a form which is then understood by the tools which process the validation and verification. So we can see there are 3 such contracts defined, and now when we run the V&V Manager tool, it sends it to the verification server, and after he responds, the results are displayed. So just to give some account of how the work proceeds, the green use cases are, at least to some extent, implemented in the AMASS platform, but there is still, for instance, lacking the association of the Simulink models to blocks, so that we can really verify those against the contracts. And also there is plan to make some finer level decision about which verification technology will be used. So that's all from my side. Thank you for your.
Okay, Pete. Thank you. Final request for any question regarding this last section or any other topic in the session? No? Okay, so thank you everybody, thank you all the attendees, thank you all the presenters, and okay, thank you for attending this session. Thank you very much.
Thank you. Bye.
Thank you, bye.
Thank you, bye.
Thank you. Bye.